Yes, thank you. I'm very excited to talk to you all about foundation models. There's been a number of talks that have been extremely relevant to my topic, actually, over the week. But the most immediate recent, well, no, actually, Adam's this morning was even more. But Omar's yesterday had said something that was very inspiring for my talk. He said that he was going to try and not just have his talk put health in the title and then be about something else. And then I realized, unfortunately, that for a lot of my talk, it will seem like I just did that. So I said, okay, I'll take the health out of the title. I'll be inspired. And I'll say that this is maybe a better title. And as you'll see, I'll argue that this is important for health, that we need to have some notion. Foundation models is a term. We all use it at this point, but we need to know sort of what it means. We need to give it a definition. And then a little bit later, Omer said that everything interesting that we study has more than one definition. I said, oh, no. So now I changed it again. So now we're going to make it not interesting. We're going to give it one definition, and then it'll be productive. Yes. No, I agree. I think the interesting parts are because of the ambiguity. So we'll explore that ambiguity today. That's something we'll look at. In the spirit of making it uninteresting and doing a good talk, I'm going to tell you everything that I'm going to tell you in advance first. That way you have a sense of where we're going, and then we'll go into the details. So in particular, the first thing I'm going to do is I'm going to argue that we actually need this definition, that we use foundation models all the time, and we don't really know what we should expect it to mean if we see it in a paper, and that this causes real challenges. And then I'm going to identify what I would say is a good definition. This is actually a very mathematical, sort of precise definition. So at some points I'll be much more hand-wavy, and some points I'll be much more precise because this is a very varied audience. But please ask questions throughout at any point. Hopefully it can be intuitive. And in particular, to make it really intuitive, I'm going to tell you what this definition is now. That way you're not surprised to see it coming. Not that it's a very surprising definition, but really what I'm going to say, and we'll see this in much more detail later, is that if we care about a whole bunch of different tasks that we're going to study in some machine learning setting, in particular health, then whereas we might think of a classical machine learning problem, is this? Nope, that's not it. Whoops. Oh, this is the laser. We might think of a single task model as we go from x to y, and we just have some function that maps x to y. All I'm going to do to make something, to talk about foundation models, is I'm going to say, really, we need to know what our space of all possible tasks is. Just like we know what our space of all possible x's are. We have some notion of a data set. We need some notion of a task set. And then once we do, we think of a foundation model as something that takes in both the data point and the task and predicts a label specific for that task now. But otherwise, the picture will look very similar, right? Unless this seemed like a strange definition, I'll tell you again in advance, this is actually exactly how we use the best examples of foundation models today, which are language models, right? If you're asking ChatGPT to categorize a movie review for you, you're implicitly giving it the task you want it to do as part of your input and the movie review, and then getting your answer out in one single sweep, okay? So this we'll see this in more detail, but this is where we're going. All right, so why might we do this? Why do we care? Well, I think this actually lets us do a bunch of useful things. So one is it will give us some ability to talk about different properties that domains might hold, and those properties will tell us recipes to how to build a foundation model. It'll also let us realize connections with other domains, other kinds of models people are exploring in AI, and less sort of application connections, more theory connections. Particularly, there's big connections with fairness that we'll see later. Let us be very concrete about why foundation models are useful. What are their actual strengths in addition to the hype? And it'll let us ask interesting questions. Really, I don't have many answers in this talk. I apologize in advance, but I have lots of questions that maybe you all can help me figure out the answers to. But let us make our questions precise, which is useful. Now here's the health part. And honestly, depending on time, we'll see how much I get to this. But increasingly, the more I think about this space, and really my background is in computer science. I did my PhD at MIT on representation learning for health. It's very clear in retrospect, which means it's very biased, but it's very clear looking back that machine learning, almost all of the successes in machine learning have some strong intrinsic connection to these ideas that come up in foundation models, to understanding the geometry, the inductive biases in a space, and how we can leverage those and do things good. So I would argue that foundation models, as overhyped as they are, they really are sort of the destination we're aiming for in machine learning AI research, to fully understand a data domain. Not only that, but I increasingly believe that this is a necessary goal for us in health and biomedicine, especially as we look away from just predict one thing on one patient's medical image or medical report, but instead predict something about a patient with all of the gigabytes or terabytes of data we might see about them across genetics and transcriptomics and clinical and wearables and social media and all of these different sources coming together. I think we need some of these innovations. So I'll touch on this a little bit as we go throughout, but that's where I see these things coming together in a very, very real sense. Yeah, so without further ado, let's actually, now I told you what I'm going to tell you, so now I'll tell you what I'm telling you. So what are foundation models, right? And here I'm going to start with a very imprecise definition, and we'll work towards this formal definition I said before. So we all know the term, we've heard it, but what you may not know is it was introduced just in 2021, 2022, depending on what date you look at, by Stanford, just across the bay here, on their Center for Research on Foundation Models. Now you might notice that they called their center the same thing as their term, so they had a vested interest in this term. But they said basically this. They said models that are trained on broad data that can be adapted to a wide range of downstream tasks. And they identified that these have a yet understood or yet incomplete character, right? They didn't know fully. But the things that they identified as essential, well, they said generally it's self-supervision, but that's generally, not always. And they said that can be adapted to a wide range of downstream tasks. They're really highlighting two things in that one sentence. One is lots of tasks we can do all at once, and the other is adaptation. That implies something about efficiency. It implies we can do this with less data than we need to do it from scratch, right? Otherwise, what's the point? If you didn't notice, this is exactly what Adam described as his foundation model that he was aiming for before. So he gave a great intro to how to think about foundation models for my talk. So this is what they had said. And because this is this is a diverse audience, I want to go through an example of how this notion contrasts with other kinds of machine learning, just so we're all on the same page. And in particular, I want to bold something. No, okay, so here's our example. I want to show that this notion really exists on a spectrum of what we do in machine learning otherwise, right? We can imagine we start from what you might call classical or traditional machine learning, and we go all the way towards foundation models, right? And we can ask what changes on this and how it relates to that definition. And it's pretty easy to make a nice spectrum here, because the first thing we can do is we can say, just like I said at the beginning of the talk, this classical model, really it means I have a bunch of x's and y's, and I'm just trying to go from one x to one y, and that's the only relationship I care about. Right? Whereas these foundation models, we want to be able to do this adaptation to downstream tasks, so we can say for any reasonable downstream task, we can predict it without new training or with very little new training, right? So this makes them seem like these are very different, but if I just rename these slightly, if I call this, instead of classical, a single task model, because it can do just one thing, and if I say instead of a foundation model, this is a zero-shot model, a model that can solve an arbitrary new task with zero training examples, hence zero-shot, then this gives us a hint that there might be things that live here in the middle, right? In particular, we can say not just single task, but what about something that's multitask, right? We can say not just zero-shot, but what if something that takes a few examples, or maybe even many examples in a pre-training, fine-tuning setting, right? So we can see that there's one or maybe two directions, depending on how you look at it, that we're progressing on here. Now again, this is a diverse audience, so I want to give some very basic examples. What does that was strange. Did you guys see two images there? I have no idea. There must be another image underneath one in the slide or something. Yeah, so what's an example? Suppose we have some images here of dogs versus cars. A single task model lets us just say, is this a dog or a car? That's our only task, right? Now, of course, we could have a different task. This is a silly task, but we could say dog or car. It's binary. I'm going to generally assume every single task in the world is binary. This is obviously a restriction. It'll be very convenient, and it doesn't really change too much theoretically. But yeah, so we can say dog or car. That's it. Multitask is very easy. Now I can say not just dog or car, I can say happy or sad. Right? I can say is this a happy picture or a sad picture. I'll tell you as an aside that my first draft of this slide, I had the dog being sad and the car being happy, and that was a big mistake. Okay, so we should all be thankful for revisions. So yeah, so we have this task, and what's clear about these tasks is that there's not really something that you would call like understanding happening of the domain here, right? If you met somebody and all they could tell you about a picture was whether it was a dog or a car, or whether it was happy or sad, they can do just those two tasks, you would say you do not understand images, right? There's some gap there. But as we move forward, we'll see that this sort of fuzzy property gets a little bit more deep. So few-shot learning, or transfer learning, that was a little harder at first. I wasn't sure what to put on the slide to show that, because it's normally a sort of algorithmic process. And then I realized this is a medical setting. So it's actually a very nice example. I can show an image of something like this. This is an X-ray of a hand. And all of us here, in principle, we could do the other tasks. We could recognize dogs or cars. We have basic training on images. But only a subset of us, certainly not me, but maybe some, could look at this in a clinical setting and say, oh, this patient has this fracture, this injury, right? So some of us have gone and done the fine-tuning process, the transfer learning process in medical school to understand these images, right? So you have to take some additional time to learn these, but it's much more efficient than if we took a baby before they saw anything and then had them try and learn to do this, right? Although obviously there's a little confounder there, but yes. Our foundation models, though, are a little bit different. Whereas transfer learning, we said there's this extra process. A sort of prototypical example of a foundation model can do is kind of anything under the sun that you ask it to do. Or that's what they seem, sort of in a fuzzy sense. Right? And so as an example, you could take this picture of our happy dog, and you could ask ChatGPT to tell you like a Disney Plus show story for it. And it'll give you this wonderful moving tale about the cinnamon and snow husky, and it'll go into great detail. But so this is sort of the natural sense of how they look, right? So I want to give just very quickly one example to show how can we actually think about making this more precise, right? Because it's one thing to say you can do anything, it's another thing to realize, oh, actually there's a procedure that we can do to do this. And the natural example is language models, right? So language models, like ChatGPT, if you're not familiar, the way they work is all they do is they predict what word comes next in the sentence. They're trained on a huge corpus of text to just answer that one question, what word comes next. So if we have a sentence, the dog wagged its tail, then a language model first says how likely is the sentence to start with the word the, and the dog wagged its, and so on and so forth, all the way through the text, right? And every time it's just saying how likely is this word among all other possible words, right? And if you solve this one task, the neat trick that language models use is that you can use this to solve any task in natural language, right? Because you can just ask, if I reframe the question a little bit, I can find some next word that will tell me the thing I care about. If I want to predict the sentiment of a movie review, I can say, the movie was great, and then I just add the word I, and I say, does it say liked or disliked more, right? I can do something like this. So that's a sort of nice qualitative definition. I want to contrast it with two things to illustrate this problem. What are these models practically? And here I want to show two things. So one is, first they're the things that the foundation model companies sell us, right? Any product that ChatGPT or Gemini or Anthropic releases, they're going to say it's a foundation model. Almost all of these, though, they're basically language models, maybe with some image or video language model in there as well. So they're all sort of satisfy this generative sequence of language, right? Unfortunately, foundation models aren't just the things that companies sell us, they're also the things that we sell via our research when we get grants and go for paper publications, right? So these are just a collection of papers that talk about different kinds of foundation models in different settings, and they're basically all pretty radically different in how you might think of them, right? So these DNA foundation models, for example, for genomics, this is actually a review, it talks about many of them, and they're basically all generative models over DNA sequences. So instead of predict the next word or predict the masked word, they predict the next DNA base, right? It's very unclear to me, and to my understanding it's very unclear to the community, why you might expect that generative process to actually answer questions about DNA that are relevant clinically. It's not if somebody knows the answer, you can please tell me, but it's unclear to me.
Why do you need DNA?
No, I'm not saying why you need it. I'm saying if I tell you I have a model that can, I hide these bases in DNA sequence and it can give you a good guess at what goes there, why does that let me answer questions about disease perfectly? Yeah.
Yeah, sure.
Because sometimes, if you look, for example, as during evolution or in the general population, when something is rare, it can be because it's, you're dead. Maybe so.
Yeah.
So that's a way of having a proxy to the deleteriousness of life. It's tough, but it's one proxy.
Yeah, you get. I'm not saying you don't get any information, right? You get some signal. Depending on how you frame what you're masking, you get a sense of evolutionary conservation. But it's very, very different than the language modeling case, where I can ask any question I want and I have a clear reason to expect it to work. But this is these models. They're generative in this way. This model is not generative at all. It uses a random selection process to pick a collection of medical events and predicts the time to those medical events after the end of a record. And they specifically design and evaluate it for use in linear probing. So only fine-tuning use, only this way. Very different sort of thing. This model uses a partially generative model. But the interesting thing about this is a foundation model restricted to a very specific task, which is sort of an interesting question. I'm not sure exactly what that means. And this model, this is not actually an anonymous paper. This is from their preprint, but it's released fully. This is for Boolean programs. It's a very, again, it's a multitask model designed to do various things. So there's lots of different things that we call foundation models in practice. Often, there's limited theoretical justification for exactly what tasks they cover and why that task set is covered to a great degree. Okay. So does it matter, is a natural question to ask. I would say so, because if we think of all these different properties, then you can find a foundation model that seems to claim foundation modelness just because it does one of these things. And you're expecting one of them and the paper does something else, then you're not going to meet the guarantees. Right? Now the one that I think is important and that we should care about is this one. These other ones are interesting, maybe useful, maybe they're correlated with each other, but this one is the one that I think we should care about. So if you disagree, that's fine. We can disagree on all interesting definitions have multiples, right? But from here, when I say, is this a good notion of a foundation model, I'll be saying, this is what we're trying to capture. Okay? Yeah. So how can we do that? Well, to realize how we'll do this, I'll note something. First, I'll note that if you try and take this notion and make it a formal definition, you might draw a picture like this, where you say, oh, we're going to have our function go from a domain X to some, such that we can use it to solve arbitrary downstream tasks, which means you're basically not saying anything mathematically. You're just restating the goal. And you can't really draw a nice sort of operational picture because we have just an infinite set of y's here, and it's very imprecise. Right? So we'll see how we can make this better. So I want to start with some notation. Maybe I should have started this earlier in retrospect, but some notation. So we have our data domain, X, normal. We often use X. If we say that we have some task Y, again, we're going to assume their binary classification. Then we're going to try and predict these labels Y from our X's. And we'll use F to denote our model that will predict the probability of this task. So we'll try and approximate the sort of posterior probability. With this notation, a single task model is just the picture we had before, something that goes from X to Y, right? The first thing I want to note is that all this notation is very standard, but I would argue it's actually missing something very fundamental in machine learning that we don't talk about. In particular, we're missing this notion of what tasks do we actually care about in the domain. Okay? And increasingly, I think this is not important to just foundation models. It's actually important in general. And the reason why is because I showed you this before, and I said, oh, we're trying to ask, dog, car, happy, sad. If I hadn't asked happy, sad, if I had instead asked, is the number of pixels that are more red than green a prime number? Everyone would be like, what? This is not a reasonable task to ask for images. This is not something we care about, right? So implicitly, we know that some things we care about and we're sort of allowed to study and call ourselves working on images, and some things we're not, right? The same thing applies to genetics or health data or all sorts of things. Some things are like, oh, this is a nice prediction task. Maybe it's not always clinically useful. Maybe we have to be careful how we use it, but they're sort of reasonable, and others are just like, what are you doing, right? I want to know something important. We talk about inductive bias a lot in machine learning. We say algorithms are good because they have the right biases to learn efficiently. This question of what tasks do we allow exactly determines what that set of inductive biases are to a very significant extent. No, sorry, not exactly, but significantly influences this question of inductive bias. And as an example, when we say dog or car or even happy or sad, we're asking in some sense about object recognition, identifying some part of an image that qualifies as the object of interest. That task implicitly in images is translation invariant. If I move the dog around, it's still a dog. It's also scale invariant. If the dog was farther back and thus smaller, or closer and thus bigger, it would still be a dog. Those relationships are fundamental to why convolutional neural networks work. If I said, oh, count pixels if they're more red than green, it does not obey those relationships. We would need a different kind of model to solve that unreasonable task. And so this notion of tasks that are important is actually deeply connected to why we build models the way we do. We just don't talk about it. So let's do this. Let's imagine that we have this notion of our tasks of interest. I'm going to call them alpha, where the set of all tasks will be A. The reason I'll do this is because it might not be like I have 20 tasks. It might be I have an infinite number of tasks, right? I could have a task for any different kind of duration and time I want to predict something, for example, right? So we use a potentially infinite, or not infinite, but unbounded index. And here, again, we'll assume that all our tasks are binary just because it'll keep our notation simple. And we'll just add this to the picture. If we do this, this does not change our single task model at all, really. We just have to superscript this and say, oh, this is our F specific to alpha. That's the only change. But now we can actually do our foundation model very explicitly, because before we had this like y1 to y infinity and it was all ambiguous, we didn't know. Now what we're going to do is we just take the index on y, and we're just going to put it as the input. And from a computer science perspective, not a machine learning, but just a computer science, this is just, we're identifying that if we have a big set here of things we care about, we're indexing it with an index variable, right? And this is an important thing to keep in mind, because I'm not suggesting that we need to train all foundation models like this. You should think of this like a system, not necessarily a single model. The model might be hidden inside, right, in some way that we'll train. But if we think of this as the system, the fundamental API, it'll give us a lot of power, mathematically and otherwise. Okay? So this is, so far maybe this will seem like, okay, you could do this, but why? We'll see the why in a moment. But before we do, anybody have any questions on this notion? Okay. Oh, yes.
Is there you mentioned something that I didn't think about it before, but it was really important. The space of tasks that are relevant and those that are irrelevant and so on. So is it well formulated with respect to the data? So saying, the data is this type or this flavor. So this will be the space of the tasks that are relevant, and those are outside of the game. So some kind of border to the type of task. I mean, intuitively I can say what the good ones and what's non-relevant, but I'm trying to think if there is much more formalization there that you can apply.
Yes, so I think that's a fantastic question. I really think that's one of the most impactful questions that I am thinking about coming out of this line of thinking. And I'll emphasize, this is actually a new line of thinking. There's not even a preprint for this yet. So please, please feel free to ask questions. There's lots of interesting things here. But so I'll note two things to what you said. So one is this space of all tasks sort of determined by your data? I think yes, to a significant extent, but in a way that we don't formalize often, right? And when I say this, we have to be very careful, because if I say my domain is images or natural images, that implies a lot about the task that you're allowed to care about. If I say my domain is grids that are 256 by 256 that have numbers in them, which is exactly how we encode images, it implies something very different, right? So really what I'm saying is it's not that the X implies the A necessarily. It's that when we say images, we're implying both an X and an A, even though we haven't realized that. And this also means that we can say something, and there are multiple different A's that might be reasonable. So I can say, or there's sort of a hierarchy in some cases, right? I can say images, and then I could say medical radiographs. Now you might agree a medical radiograph can be represented as an image, but the tasks that are of interest there are very different. So are the images, of course, but the tasks are also very different. We saw that in Adam's talk as well. By some, dilation reflects different inductive biases and the kind of attention he was using. Yes?
So basically the idea of this formulation is that it gives you a notion of getting into a subfield, let's say the medical images, and ask what is the performance within that subfield or that context?
Yeah, it allows you to be specific about the scope of tasks over which you're expecting generalization. You're saying, oh, my model is good at many tasks. Which tasks? Right? It's these tasks. And in particular, these tasks in line with some distribution. Right? Now, we may not know it. We may not be able to write it down. We may not be able to sample from it necessarily, but we imagine that it exists and we can work with it in various ways. Right? So in particular, before we had sort of two very ambiguous things in our sort of word definition of foundation models. We said arbitrary reasonable tasks. Well, now we can be very specific. It's exactly reasonable under this notion. Right? We said sort of data efficient, which I put differently here. So here we're sort of implicitly assuming something like zero shot. You can actually work in pre-training fine-tuning into this. It's just a little inelegant, but we're sort of implicitly assuming a certain kind of data efficiency here in this formulation. So that's what changes here as we do this. But this is nice because we should be specific about the tasks about the claims we're making in a paper, in my opinion. And more than that, it lets you change your notion, right? So if I say, oh, this is my foundation model for DNA sequences over the space of tasks that are related to evolutionary conservation, then maybe that generative model is actually a very reasonable model for exactly the reasons that Thomas said earlier. If I say my space of tasks is any interaction between genome and disease, then maybe not, right? So it allows us to be more specific in how we're discussing things. Okay, so what else does it let us do? Also, I'll note, this is already how we do language models. Right? I showed this picture before, but you ask ChatGPT a question, you're telling it the alpha, you're telling it the X, you're getting the answer. Right? So if this feels unfamiliar, this is exactly what we're actually already doing with the things that are most unambiguously new, exciting foundation models. Okay? So what does this let us do? So first, there's something that people very deeply in this field sort of already know, but is often misrepresented in the popular press. And it's about performance of foundation models, right? So in particular, if we imagine that we have this set of all models that are good for some task alpha, right? Then this set f alpha 1, this is all the models that are good for just one task. So this is like a single task model just for alpha 1. And this might be just for alpha 2, another single task model is just for alpha 3. Well, the foundation models sort of have to live in this intersection here because they have to be good at all the tasks, right? So this tells us that actually foundation models are not like a bigger thing than single task models. They're actually a subset of single task models. Any foundation model you can say is a single task model for your special task, but not the reverse, right? So explicitly, this tells us that if we ask about the best possible performance you could ever obtain in a task, a single task model will always match or outperform a foundation model, right? And not in an interesting sense, just because if you say, oh, I have a better foundation model, I'm like, great, that's my new single task model, right? Many of my theorems will just be cheating like this, bookkeeping, but it's important, right? Because it's not actually that we're pushing performance. We're pushing something else, right? And what is that thing? That thing is what I'll call, I should have updated this actually, but what I'll call task-specific data efficiency, okay? That's what we're pushing. Okay? Yes?
So if I put down my pure mathematician's hat, then there's also a need for existence proof.
This is true, yeah. I'm missing some of the math. You are correct, yeah. And actually, there's another mathematical problem with this, which is I haven't said what criteria over performance on all the tasks you need to qualify. So it's actually possible that you can be a little bit bigger than this, depending on how you classify things.
And also implicit, it's like the foundation model shouldn't just have to beat some random task mark or something, right? You can also do something, intend to do something, but doesn't mean that you have to put some qualification on this to do something useful for this task.
This is true, yeah. And as I said, there's a preprint in progress, and we're trying to figure out some of the formalism here. So think of this as informal. What I will say is that I think we should be comfortable with some degree of the ability to make really stupid foundation models. Because we can make really stupid single task models too, right? I can say that this is my single task model and it's just a random predictor, right? Or I can say my single task model over my data set X, but my data set just has one data element in it, one sample, and that's all it will ever have, right? What we need to be asking about is sort of how do we think about what they're, what the systems they are, and then we can ask how good are they, and what are meaningful sets of foundation models that meet some performance criteria. And we'll see some specific ways where you can construct foundation models that meet those criteria up to the degree of certain learning algorithms that are already characterized later. So we'll see some, but you're absolutely right. Yeah. Okay, so they do push the state of the art on task-specific data efficiency, right? So here what I'm showing is, imagine how much task-specific data you have here, where you could imagine going out to an infinite amount of data, as we do. And your performance per task, where we're just going to pretend that this is like random chance. I just predict everything at random. And this is like the best you could possibly do. So like the Bayes error for the system, right? And you should ignore this line in the middle here because it's not actually a concave curve. But we can imagine plotting something here. We can say, oh, if I make all my traditional single task models, I might make a plot that looks like this. As I get more data, I do better, right? I approach perfect as I get infinite data. And what I'm claiming is that foundation models would draw a curve like this. Okay? So it's not that we're pushing the Bayes error because that's something we can't change. What we're doing is we're saying that, oh, I can get to the same degree of performance as a single task model, but with much less task-specific data. Okay? Now, if you've been paying attention, you might be wondering, wait a second, aren't I cheating? Because I just told you foundation models are all subsets of single task models. This shouldn't look like this, right? So again, most of my proofs will be bookkeeping cheating, right? So what's the cheating here is what counts as task-specific data is something very different if I say my model is only going to do one task than if I say my model is going to do a whole bunch of tasks. Right? If it's going to do a whole bunch of tasks, then my data, which is the same size, is spread across all those tasks, so it's less task-specific. If I'm going to do just one task, it all has to count for that task. Right? So what this means implicitly is that if we ask about total data used, we get a very different relationship that we don't care about, right? So foundation models are not more efficient in terms of total data. They're not more efficient. They're not better in terms of performance. What they do is they give you task-specific data efficiency. Now, no, this is nice, especially in healthcare, because this is the thing we care about in health and biomedicine. We have lots of data, actually. We have very little data that's specific to the task we care about. We need to learn how to leverage it. It's also sort of what we care about in machine learning in general, right? We want to push up towards here. That's where we want to go. There's other senses in which foundation models are generalizable specifically in this notion, but they basically all reduce to this one. Something that's a little bit different that I want to highlight is they also shift things on accessibility. And this is something that's very obvious with language models. Like this is from a paper where they ask about people using ChatGPT to manage their own medical care. But it's actually something more general about foundation models that this definition lets us realize. And in particular, foundation models are more accessible because they're more accommodating to human uncertainty in the task of interest. So what do I mean by this? How many of you have done this with ChatGPT? You ask it a question, and then ChatGPT gives you like a good answer, and you're like, no, actually, sorry. I didn't mean that question. I meant this other slightly related question, right? I do this like all the time. I imagine many people do. What we're doing is we're saying, oh, here's the task I think I want. We see that the model is pretty good, but then we realize that we actually care about this other task. It's a little different, right? So we're shifting, we're moving in that space of alphas, right? If I have a foundation model, if I have a foundation model, then by virtue of knowing that it exists in this sort of continuous system, I should expect a greater degree of continuity over this space of tasks. Whereas I don't get the ability to make that expectation for the single task model. So depending on how you produce it, of course, we need to be formal. This is, again, very informal. But there's a reason to think, oh, there's some relation to accessibility because of uncertainty in our tasks. Again, in healthcare, we care about uncertainty in tasks quite a bit. So here's something that's really interesting. This view says something very nice about why it's hard to evaluate foundation models. In particular, if we think about evaluating a single task model in aggregate over a whole data set X, this is kind of easy, right? I can make like my confusion matrix, I can compute AUC. If I only care about it across the whole data set, I'm sort of done in a decision system, really, if I just do this. When is this hard? This is hard, as we've heard in many great talks, including the one just before this and others. This is hard in fairness settings, right? Now here is my not fairness person notion of why it's hard in fairness, so please correct me. But it's hard in fairness because we don't just care about the aggregate picture. We've taken our whole space and we break it down. We've partitioned our input into lots of subspaces. And we ask not about the overall performance, but we say, I care about performance on all of these partitions at the same time. And maybe their intersections too, right, in some ill-specified sense. Why is foundation model evaluation hard? It's hard because I have this bigger input space that I partition into different tasks, and I care about performance on all those different partitions at the same time, in potentially an ill-specified way. So whereas in fairness, we partition our input space by subsets of people, if we think of our input space as all people times all tasks, now we need to partition it by task. And we have many of the same challenges as we do in fairness. Because it's not an aggregate, it's now this, we care about everything at once. So there's open questions here, like things like, can you do multi-calibration over foundation models, and what does that mean precisely? And you need to generalize it slightly, but there's a clear analog, I think. Or the impossibility theorems. Are there impossibility theorems for foundation models? Can we not have them be simultaneously calibrated on all tasks and simultaneously give us a sort of a similar performance in some way? I don't know, but I think they're interesting questions. We can also go the reverse, actually. In foundation models, something that's pretty well accepted is if we deploy these in healthcare, we can't evaluate once and stop. We have to do continuous auditing, continuous evaluation, because the space of tasks is so big that we could always see something we haven't anticipated, right? Does that suggest, in fairness, that if we think about a sufficient number of possible subsets of people, that we should not be saying, I can evaluate once and stop, but I should be continuously auditing my model across different patient subpopulations to see how performance works, because there's always more intersectional identities? Again, I don't know, but I think there are questions. Okay, so let me get to something more practical, something where I do have some actual answers. I said that we can use this to build recipes, so let me tell you what those are. So in order to do this, I'm going to give you some properties. So you say, oh, I have my space of images or EHR data or genetics. That domain gives me some notion of what my tasks, or what my data and what my tasks are. These are properties that apply to those domains. So there's two. So in Bin's talk, we learned the word veridical. Right? Yes? Okay. Here we're learning this word intentional, not spelled wrong. This is actually spelled correctly with this S here. Okay. Before I called this something else, but ChatGPT told me to use this word, so it's definitely right. So intentionality is a question about how can we represent tasks. Right? I've just been saying a task. I haven't told you what this means. A task is intentional if you can represent it in an explicit sort of parametric representation. Right? We'll see an example of this in a moment. I can also talk about reducibility. I can say that I have this big space of all tasks. Maybe I can squint and pretend that it's a much smaller set because I can use some smaller options to solve other tasks. Right? And I'll say it's universally reducible if I can go all the way down to just one task. Right? So these two properties, yeah.
You require that every single task can be a single.
So these properties are things that may or may not hold in the domain. So I'm not requiring anything. There are many domains where these properties do not hold. What I'm going to say in a moment is if these properties hold, then you can do this thing, right? But for universally reducible to hold as a property on a domain, then, and I have a more formal version of this, you need to in some way, meaning actually algorithmically, like computational complexity style, you need to be able to reduce the task in the domain down to a single task. Canonical example, language. Language is actually both intentional and universally reducible. That's exactly why large language models work. Okay? So the intentional is I can write the task like this. Universally reducible is language model completion, next word prediction. Okay? Now I'm going to show you that this applies to other domains too, but I'm going to tell you in advance these are not the only properties. There are other properties where we can build very different kinds of foundation models that we'll see later. So don't think I'm just telling you about language models again. But in particular, language models is not the only domain that satisfies both of these. And any domain that satisfies these two properties, you can build a foundation model by solving that universal task. One example of this is actually electronic health record data. So this is where that health connection becomes more than just in the title. Over the last 2 years, actually, we've seen the emergence of these autoregressive foundation models for EHR data that work very much like language models do. We recognize that what do we mean by electronic health record? We think of it as a continuous timeline of, or a longitudinal sequence of continuous time events. And we say much like in natural language, we ask what word comes next. For EHR data, I can ask what observation comes next in the record and when does it happen. If I can solve this task, then I can answer arbitrary tasks about the patient future in a very similar way to language. Okay. I won't go into this in too much depth, but what I'll say is how might this work is we take the patient's medical record up until a point, and then I generate possible synthetic futures just by repeatedly auto-completing what happens next. And then if I want to, for example, predict whether this patient will have knee pain recur in the next 30 days, I just look over all these different trajectories and I ask, in what fraction of them does that knee pain recur? And in this patient, maybe it's 2/3. And I say, oh, okay, I'm going to give a prediction of 2/3. That's the likelihood that this patient will have this knee pain recur within 30 days. Right? This kind of model is not just a theoretical. Over the last 2 years, it has become very clear that we can actually build these. There's a number of different papers, including some that I'm involved with, but many others in the community that build these and show that they actually work well. And amazingly, they do this not on huge data sets. So for a long time, the sort of health AI community has been saying that we think we sort of overuse the MIMIC data set. We can't do any more. And you can do this on MIMIC. You can actually get meaningful zero-shot performance on arbitrary downstream tasks on publicly available data sets for EHR. Very surprising to me and others in the community. It's not just in academia either. This is coming for actual health systems. Epic has built one of these models. They call it Curiosity. They used to call it Comet, and then somebody told them, we'll sue you, and so now they call it Curiosity. But it's a very large-scale model that does exactly the process I described before, and they profile it on a wide range of tasks and show significant performance improvements. Okay, so this is not a hypothetical. Now again, you might be thinking, okay, great, I've described language models. We already know about language models. What's interesting here? What's interesting is that this is not the end of foundation models, right? There's actually lots of problems with this recipe that exists in different settings. And we might want to do better for various reasons. So one problem is that this approach may be very much suboptimal. Okay? It's not actually hard to see why it's suboptimal, especially for EHR data, because it turns out that generating these is actually very expensive. Now, there's lots of work happening like right now to make this less expensive, but with a sort of classical naive approach, not fully naive, using some of the optimizations, it might take like 24 hours to generate enough trajectories to do your zero-shot inference for a task. Just at inference, not training. This is like make a prediction. It takes a very long time. This is not just a computational expense, it can be a statistical expense too, because every trajectory I generate, every event I generate rather, is an opportunity to compound errors, to make another mistake in my prediction. Yeah?
Just a verification question. When you say foundation model for electronic health record, you actually mean a generative model that generates electronic health record and then applies the learning algorithm on it, or?
There's no, so this is truly zero shots. There's no learning algorithm that happens on these trajectories. So I do mean foundation model in the sense that I'm describing it. The space of tasks here that's of interest, my A, is anything that you might predict that would show up in the EHR data about the patient in the future. If you want to be very precise, you say anything that you can deterministically read out of the EHR data from the patient's future, not their past, but their future. then under the assumption that I have the perfect generative model, then you can use this just like you can in NLP to produce a zero-shot inference. Yeah. But it does have these problems that, okay, so it has a couple, one problem is it's expensive. It's actually a tiny bit statistically biased. I won't go into why. But language models aren't, but these kind of models are for a very sort of strange, not strange, but small mathematical issue. But other than that, they're good, right? So they're statistically expensive, they're computationally expensive. Why are they statistically expensive, or why are they expensive, period? It's because we're training them to learn just the next thing. And in medicine, it turns out we often don't care about what happens like immediately next. We care about things that happen in the future, like years, right? And so it's very expensive to try and go over all of these different events, right? I have to marginalize, there's this sort of compounding of errors, there's this combinatorial growth of my distribution. It's a big problem. Okay. So what can we do differently? Well, let me tell you a different recipe. Okay, so that's the universal recipe. Okay, so the other thing is there's other domains. It's not just all EHR data, right? We won't always have universality. Okay. In particular, so far we talked about natural language and EHR data. Here are two other domains that we commonly study: small molecules and protein sequences. Okay. In both of these domains, I would say that they don't seem like they're universally reducible. This is my assertion, so it's speculation. It could be wrong. And I'm not sure if you can call them intentional. I can't think of any, but I'm less convinced than I am about the universality. Yeah?
Can you explain the problem with this, not the next one, but
Oh, yeah.
Just like explain why I'm confused.
Yeah. So
if I don't care if something happens in the future, I can run many times and see how many times.
Absolutely you can, right? But the thing that I'm actually pre-training the model for, the loss, is always about predicting this, given everything I've seen up until now. It's never about predicting a marginal over this. That doesn't mean that if my model here is perfect, then you're fine. But any small problem in this model will magnify into a larger problem when I do this unrolling process, right? There's also a harder limit on this, which is that we can't look at the entire history. We can only look at a subset of it, right? And so if I want to predict something that happens way down here that has some dependency on this event, then in order to ever see any relationship in my generative outputs, my model needs to have a big enough context size that at some point I could have been predicting this next event and have my history go all the way back to here. And that's not necessarily always true. Does that make sense?
I think so. The first one, I was wondering, okay, but language models, I can also worry that errors
You can.
kind of accumulate.
Yes.
The other one, you're saying, okay, these other events need different context, wider context somehow.
So to be clear, actually, both of these problems apply to language models. They do. It's not that this problem does not affect language models. It's that we can't do better in language, as we'll see in a moment, at least not to my knowledge. It is worth noting, though, that in language we have one advantage that we don't have in EHR data. In language, I don't need to make a calibrated estimate of something occurring. In EHR data, I want to know the probability that you're going to develop cancer in 5 years. That might be very small. It might be 1 in 1,000, 1 in 10,000, right? That means that if I go back here, I need to generate a huge number of trajectories to see that, and they all need to be calibrated. In language models, we much more often, and this is explicit in how they work, we ask about, give me one very likely trajectory. I don't care about calibration. So that approach makes it much cheaper in language, but it's not what we want here. Maybe it's not what you want in language too, but it seems to be working fine. But it certainly wouldn't for EHR data. Okay. But the bigger reason, though, as we'll see, is we can't really do better, right? So I said that we have these new domains. They don't satisfy these properties. So I'm going to introduce more properties. Okay, that way we can talk about them. So here are two other properties. So one is this distribution, this data domain might be what I'll call sampleable, if I can actually draw samples from my task. Okay? Now in practice, we can almost never be able to do this. So we might have a weak version where I can say I can draw samples from a distribution that sort of covers my space of all tasks, right? It might include other things that I don't care about, but it'll at least include my tasks. And I'm going to have this one that's a little fuzzy called indirectly evaluable, where I'm going to say, maybe I can sample labeled examples for a task. So if you tell me your task alpha, I can draw a pair X and Y that's sort of in some meaningful sense, and I can make this more formal offline, but in some meaningful sense cover your distribution X. Okay? And we'll see an example where this is true. Okay? But these are two different properties. It turns out, of the domains we've talked about, EHR data actually satisfies all of these properties. I'm not aware of any other domain that does. Language does not satisfy these other properties. I don't know of a way to sample tasks. Or you could do a very weak sampling that would be extremely diffuse. But they're certainly not indirectly evaluable, necessarily. Not in the way that EHR data, as we'll see, is. So it turns out that I can give you another recipe. Any domain that satisfies these two properties, you can also build a foundation model. But it looks very different. It's no longer going to be generative, in fact. What we're going to do is we're going to randomly sample tasks with our two properties. We're going to get the task and a label and an input for that task. And then we're going to train the model to take the task explicitly as an input and the input and predict the output. Right? But we're going to do this randomly. That way we cover the whole space. So what might this look like? So suppose I have my EHR data, and this is the patient's actual record, like their whole data. Well, I might say that my task will show up here eventually. Huh. No, this is actually frozen. Or just the presentation is for some reason. Apologies, folks. Okay. So we have about 15 minutes left, so I'm just going to switch to the board instead of trying to fix this. All right, so we'll just we'll wing it. Oh, no, wait. There we go. Oh, OK. Well, I'll pretend I drew this on the board, and I'll talk about this. OK, so what can we do? So first, we can sample this. You know, I said that we might have a task like this. I care about, does this patient have this knee pain occurring in 30 days? These are deterministic elements. This is an observation that can be in my EHR data. There's a set. All right. Apologies, folks. We'll use the board. Well, I'll try and hit the button, and then we'll see if it comes back. This board is better. Of course, now it's going to work. I need to stand over there, and then it'll start working, and then, yeah. Can people see this board? Yeah. Okay. All right. So we have our patient's medical record, right? We might have different medications. We might have different lab tests, and then maybe in the future at some point we have some event of interest, right? Like a diagnosis, let's say, because I can't draw the knee. So we have all of these things. Is this going to work now? Maybe. Okay. Yes. Okay. Threatening with my awful drawing skills scares the computer into working. That's the conclusion. All right, so we can actually construct this object, and we can truly randomly sample these. I can sample any possible code that might occur in my medical data, any diagnosis, any laboratory tests, whatever. I can sample different time ranges. Right? This is just a uniform distribution over two objects. And I can also take this chunk of the patient's record. And then what I can do is I can say, for this randomly chosen task, this randomly chosen patient record chunk, what's the answer? And I can actually say, if I look forward 30 days, does this event occur in that window or not? And I can get a 1 or a 0 on a static data set. Importantly, I can do this for any task here, with one small caveat that I might need to say I have a censoring option. Right? So we'll predict that too. But I can randomly sample this, and then I can actually evaluate it. So what this means is that then I can take this as my input, just this part, not the full sequence, just this part. I can take the task, and I can actually give a model, a neural network, both of them. I can give it a sequence that has the patient data and this code, this duration, and I can ask it to predict the label directly. So what I'm doing here statistically, in comparison to the generative model, is I'm not predicting all those intermediate events. I'm just predicting the marginal of this particular property over all possible sequences I could generate. And I'm doing it directly. So this is much more statistically efficient, also computationally efficient. It goes over arbitrary timescales, and it captures whatever tasks are within the scope of things I could randomly sample here. So this depends much more explicitly on what the space of tasks is, because I have to be able to sample from it. This space of tasks is not as rich as the generative models, because in a generative case, I could ask about, does this happen and then something else and then something else? Right? This is more limited. In practice, this is basically everything we ask about right now. You could also make this richer, too. It's very easy to do. But this is a constructed foundation model specifically given this representation. This is not just hypothetical. A student, Payal Chandak of Zach Kohanes at HMS, and my student, Greg Kondas at Columbia, we've been working on this. The preprint will be up so soon, but it's not quite yet. We've been calling it every query because we're sampling every possible query. Right? This is very preliminary results, so take this with a grain of salt. But if we ask about random tasks in the sense I just meant, where I randomly sample codes and durations, or actually no, I think we even have a fixed duration. But durations are continuous. They're very easy to generalize over. We've tested that as well. Then this approach will outperform autoregressive models by roughly 80 to 90%. Meaning not that it will be better than autoregressive models on roughly 80 to 90% of tasks. I'm not saying the jump is 80 to 90%. That would be insane. I'm saying that you pick a random task, 90% of the time, this approach is going to be better. Maybe 80%, depending on how you call it a fair comparison in terms of capacity. But very significant. Now, where this might differ, if we go not random tasks, but the specific subset of those pairs that are actually clinically meaningful, and the specific subsets of X's that are clinically meaningful, then it's not quite one-to-one, and we're still assessing this, but very promising in terms of actually outperforming these autoregressive models. This approach is also dramatically more efficient. I said before, the autoregressive model, it takes around 24 hours to generate trajectories for the experiments we used to do this. For the every query model, it was 20 minutes or something like this, right, for the same comparison. So there's basically no comparison, right? Because this is just a classic model, basically, at this point. We've reduced it to directly predict one output, so it's the same as it ever would be. I want to note something else. This is not just limited to these two foundation models. There's actually this whole other area of machine learning happening right now that under this perspective, you can realize as foundation models. And it happens in this interesting case where I say, what if we lack this ability to represent tasks in this intentional manner? Now, I didn't say this before, but I can say, what does that mean? Well, if I can't represent tasks intentionally, I have to represent them extensionally. That's the other, the antonym of that word. What that means is I can do it only via examples. So you say, oh, here's my task. I can't really describe it to you, but I have a bunch of X's and Y's. Okay? Now, you might say, oh, well, how could I do anything? I can't pass those into my model. Turns out that there's this whole field of machine learning coming out called prior fitted networks that are doing exactly this. So this is a figure from the paper, but it's much more clear what's going on and why it relates in this, this blog about these approaches. What they literally do is they take a bunch of X's and Y's and they pass them to a transformer, and then they give it just a new X and they ask for the output Y. Right? Now they're approaching this from a Bayesian perspective. So the statistics that they would use are very different looking, but this is exactly your alpha, your X, and then you're getting your Y. Right? It's just for a task that I can only represent via this sequence of samples, which comes with its own trade-offs, right? So you can ask lots of rich questions here about the geometry of these spaces, the complexity. If I can represent alphas in this way, this is obviously a much longer minimum restriction length, maybe an infinite one, right? So how does the capacity I use at inference time trade off between the capacity of the model? What does the geometry of the space of alphas look like in terms of how close are different sequences like this in comparison to actual sort of intentional representations? I think this could be very rich from a sort of complexity perspective. It also actually unifies. Oh yeah, please.
Is that in the training or is that like
both?
in context learning? Or?
They do this in both training and at inference time. Yeah, in both cases, it looks like this for these prior fitted networks, at least. And this is what they're actually doing here is exactly the same as the every query approach in terms of the foundation model recipe. They're sampling a task, meaning a bunch of X's and Y's, and they're passing it to the model at training time and getting the Y. And then at inference time, they take their X's and Y's like this as well on the inference data set. Yeah. So yes, so this is something that we see in practice with these prior fitted networks, which have just emerged in the last 2 years in a very different area of machine learning.
What's your 5 minutes?
Perfect. So this timing is actually very good because I've alluded to many of these questions already, in particular the fairness applications. But there's a number of different questions that come out of this approach that, I forgot to LaTeX some of these, I apologize. But there's a number of different questions that come out of this approach that are very relevant. So something that we mentioned just briefly a moment ago is there's lots of different notions of complexity that you can ask about in computer science. There's complexity in terms of how complex is it to compute a task, like an actual algorithm, like sort a list or something like this. And the language we use there is about reductions. I reduce from one task to another. In the universal approach, we saw that we're actually using that same notion of reductions now to talk about how we can do different kinds of foundation model learning. I think this suggests that there's a relationship here between the complexity of reduction of a task and the possible error we might see under it, given a different, the sort of suitability of a learning framework to learn a universal task. There's complexity here in terms of the distribution over task alpha and the relationships, the information relationships it has with the parameters you're learning. There's sort of geometric approaches when I ask about how close are two different tasks in this space. Not something we think about often. And all of these relate as well to the fairness questions too, because now our tasks are analogous to the partitions or the subgroups in the fairness settings. So actually, that's it. I want to acknowledge this is actually most of these are acknowledgments for meds, which I didn't mention in this work, but it was the driving work that led to a lot of my thoughts about foundation models on EHR data, and also a lot of these autoregressive foundation models that I mentioned out of this work on data standardization, which is very different than the stuff I'm talking about here, but leads to ways to think about parametrically defining tasks, sort of agnostic to data source as well. And with that, I'm happy to take any further questions. So thanks.
Brilliant talk. Questions?
I have a question about the EHR.
Yeah.
In practice, for what I can think of, maybe you can think of other applications. Couldn't you basically just take the model, the foundational model, and then do additional fine-tuning for everything that you're going to look at? Because I can't imagine of many applications where you want to just know what's going to be the next observation. But what you want to know is if 6 months, in the next 6 months, someone's going to have a heart attack, right? Or someone's going to. That's kind of a finite space of things that you want.
Yeah, it's a fantastic question. So I'll say a couple of things about this. So one is, I'm assuming you're talking about this kind of foundation models, the ones that have been published a couple times now. I don't think these are ready for deployment yet for a variety of reasons. I think it's going to happen regardless. As I said, Epic is building models like this on their data and sort of advertising them extensively. But we need to think very carefully about when you would use this. Now, would you use this by fine-tuning it? I would say probably you shouldn't, because the gain you're going to get over just training a model from scratch that's even simpler, like an XGBoost model, is probably going to be very small. In many cases, honestly, you train the right XGBoost model, you're going to do just as well. The advantage of this kind of approach, again, is task-specific data efficiency. It's if I don't have any labeled data, I can't do that fine-tuning. Can I make a good estimate with this approach?
Actually, there is some gain when you have rare conditions.
Yeah, so if you have if you have some labeled data, then you can do fine-tuning. It's this trade-off constantly between how much data you
If
have.
you have a lot of data,
Yeah.
is a bad example because probably it's simply.
Yeah. No, but you're navigating that trade-off identically. There are a couple of cases where I think this approach actually, in and of itself, is useful. One that we don't think about a lot for foundation models is something like automated reflex testing in hospitals. So reflex testing protocols are when you get your blood work taken at the doctor, depending on the system, they don't always actually use all of it to take the labs that they've ordered. In certain cases, there's a little bit left over, and depending on what the results come back, or certain pre-recorded system or like manually specified systems in place, they'll actually automatically run additional tests that they know are necessary based on the initial results that come back, right? You can imagine, and with Yuan Lo, actually, I worked on a paper about this. You can actually imagine saying, if we can predict that the doctor will immediately order a lab test based on these results, then we should just automatically do that reflex test, right, in a dynamic sense. And so something like this is actually very suitable for those sorts of immediate completion tasks or things like this. There's also, I think, a strong utility for this in phenotyping. Like I want to cluster patients.
I'm thinking what you're saying is in ICU settings, so you have to do things fast.
Yeah, but also from a research perspective, if you can use this to identify patient similarity across all different clinical aspects, I think this is probably one of the richest ways you could imagine doing latent phenotype discovery. The other thing I'll say is if you are asking about a 6 months or a 2 year or something like this, I would say just don't do this in the first place. Do this every query approach I talked about before, which is exactly predict whatever you want to whatever timescale you want, and you get it in one shot. So yeah. Yes?
Please.
How do you think of a multimodal foundation model in this formulation?
Yeah, so there's two answers to this. So one is we've seen a lot of multimodal foundation models, and in practice, when they actually have this generalizability, what that means is we stuck something into a language model, and then because language is universal and I can describe anything and it's compositional, you get a bunch of things for free, right? But if you're not adding language to something, or you want to learn something that's not just things we already know in language, like in medicine, that approach doesn't really work. It doesn't really cut it. From an EHR data perspective, there's a very natural way in the context of looking at data as this timeline view to imagine multimodality, which is that I can just have like this be an actual image or a clinical note or whatever modality you want can live at some time point here. And the way I actually model this can be, depending on how you design it, agnostic to that. The reason we don't see this that much is because it's incredibly computationally burdensome, and that is absolutely the next frontier. There are other challenges, but I'll stop there. Yeah.
Okay, let's thanks Matthew for a fantastic talk.
Thank you.
And just to stretch out 5 minutes, really no more, okay? For the next and last, I think, talk that is coming. So.